what we do here actually is we're metallurgical engineers, and we sell products for grinding and flotation.
So we got discussed those two installation points for the cyclone feed, for the cyclone overflow to the flotation feed, and the cyclone underflow. Is that also important?
Yes, but the when we go to flotation, I think it's really important as well, because after you spent a lot of money on reducing the particle size, now you do not want to lose particles, right? And the most of the mines, they have the flotation process, and the tails of the flotation process goes to the waste. So there's nothing else you can do. And flotation is basically a probability process. You have the particles, they will be, they have a residence time in the flotation process. If you do not recover the particles that you want, they're gonna go to the waste. So most of these mines, what they do is they calculate efficiency of the circuit based on whatever is feeding the flotation circuit and what you are sending to the waste. That math has to give you an indication on recovery.
So if there's too much material sent to the waste, to the tailings from the flotation cell, and you see that there's a lot of feed coming into the flotation circuit, you know that a certain amount of particles should be valuable materials which are recovered, or?
Yes, pretty much. But then again, you have a specific throughput, which is the variance of the throughput feeding the flotation is not really significant when I say throughput. But if you have a change in the particles, affect the residence time. So if you have a pulp density, a difference of pulp density feeding the flotation, that will affect the residence time. So you have to immediately correct that information, because the residence time can vary from 1 minute to 10 minutes. So can you imagine a plant fitting 5,000 tons per hour, and in 10 minutes, if you do not correct or operate the flotation under the specific pulp density that you need, the amount of material you're going to lose, it's huge. So flotation is really dependent on particle size, pulp density, residence time, and then the capacity of the flotation of recovering these particles in that volume that you have available in the flotation. Yeah. So, for example, we gave these the same extremes scenarios in the grinding, but when you go to flotation, if you have a high pulp density, your circuit, you cannot expand the flotation circuit. You cannot put one more cell, or you cannot put a taller cell in 5 minutes. So you have to adjust with water and airflow. So those are the only two variables that you can actually make corrections when the pulp density is changed. Yes. So and that process is really sensitive and quick. When you have a variation in the pulp density in the flotation cell, you have to correct that immediately, adjusting the airflow or adding more water, for example. So pulp density, it's on the hands of the operator to make a quick decision whether they're gonna have a maximum recovery or they're gonna lose material to the tailings, right?
Yeah. So they need to know, they need to control the density by using water, for example. If the amount of material is too much to be handled in the flotation cells, so they add water to make it the settling of the particles more efficient, together with the parameter of air injection and chemicals, probably, or not.
Yeah, so looking at the flotation cell, what you have is you have a three-phase system, because you have water, you have minerals, and then you have the air. So what happens between the water and the particles is you want to make the particles available for the air to collect these particles and move to the froth phase. So you need the exact amount of water to make that particle available. If you don't have, let's say the extreme scenario would be a high density, high pulp density situation in the flotation cell, these particles will be attached to each other. So the air or the reagents, the collector will not be visible. So the particle will not be visible to the air and to the reagents. So adjusting this pulp density in the flotation cells makes the process efficient, because you make the particles available to be collected. So this is one thing. On the other side, if you have a low pulp density, the materials be floating around, means you are not having the maximum throughput or efficiency on the system. So the both sides, you're going to lose something. There is a very tiny range of pulp density that the flotation is maximized its efficiency. You're going to make these particles available to be collected, but what about to be actually sent to the tails? So both particles has to be available. It's the same actually principle of the cyclone. Both has to be available. One goes to the overflow because it's fine enough, and the other is available, but then is going to the underflow. And in both cases, what happens is these particles, the volume is so big, the throughput usually is so big that they attach to each other. So what we see from time to time is like in the cyclone, a coarse particle will actually carry a lot of fine particles with this flow to the underflow. So that's the negative effect on the cyclone, and the same thing on the flotation. So sometimes the valuable mineral that should be collected, it's being pulled down by the tails to the underflow. So the best way to correct those two situations is by adding water. So we say that adding water, you make these particles available either to be collected or separated, or to be actually collected by the reagents and the air in the flotation.
So water is very important for the flotation process. But so by engineering design, they know by the pipe size, they know by the flotation cell size, they can calculate the amount of solids that is needed to have a right settling. So it's more like engineering calculations before they are going to control the process, and then they know what the perfect conditions are, or at least they have a certain range. Or
yes, and that's a good point. So the process management will actually work with the engineering companies to say we have to operate the hydrocyclone in this specific pulp density, like fitting the cyclone at this specific density, because we want that result. If something changes in the process, like let's say the ore type changes, these guys will actually change a little bit of this target control parameter. And then the same thing for flotation. So you can set this target. For example, I'm going to feed the cyclone with 55% solids, and I'm going to feed the flotation with 35% solids. But then you have a small room to work on it. And if we plan, or if we put into the graph, like what is the real pulp density fitting the flotation or the cyclone, I think we're going to have a lot of outliers on the points that it's away from the target. But as I said, I think most of the mines, they understand this concept. They do give a lot of credit and value to the pulp density. But the question now is how they are measuring right now, and what can be done with the equipment that you guys are selling.
And what we see now is that they use the nuclear density gauge for decades, probably like the Marcy scale, and they say this is how we do it. This is our operation. We are not going to change it. But they are not yet used to a different technology, although we have a lot of advantages over the nuclear technology. Is it also important to have it a good homogeneous mixture with a lot of water to keep it more like mixed, so that the particles don't stick to each other?
Yeah. So yeah. What we say in flotation is you need the particle suspension. So you don't want the particles to be drowned, and you don't want the particles on the froth phase. So these particles has to be on suspension on the collecting zone. And what happens is flotation is probability. So that's why we have residence time. So probability means there are three types of probability in flotation. One is the collision. So the bubbles has to collide with the particle that you want to collect. The second is attachment, because after these two, the bubbles and the particles, they collide, they have to stick attached. And the third probability is detachment, because these particles, after collect, after attach, they can, depends on the turbulence of the circuit, they can actually detach. So if it's a probability process, you have to keep the variables at its optimum value, which is you need the right amount of particles, they have to be in suspension, and they have to then be available for the probability of the design of the circuit, right?